日華牧師分享到，啟示錄早於2000年前已經預言，當世界踏入最後7年後3年半，即係世界最後嘅1260日裏面，世界會進入大災難時期，而呢一場大災難將會係全球性嘅。意思係世界將唔會有任何所謂嘅安全區域，只要係活喺地球上嘅人類都會被呢一場災難牽連。藉住過去12年間，日華牧師所分享極具前瞻性嘅2012信息，讓我哋得知呢一場1260日大災難嘅成因係 Planet X 嘅重臨。有關 Planet X 會為地球帶嚟嘅災難，其實聖經早已記載。第一次係創世記嘅挪亞大洪水，第二次則係出埃及記發生喺古埃及嘅十災。於8年前，日華牧師亦都曾經喺2012信息之 Planet X 分享古埃及人曾以佢哋嘅角度去記載呢一場十災。按住佢哋親眼所見，十災唔單止發生喺埃及，而係發生喺全世界，並且呢一場普世嘅災難係由一顆巨大嘅行星逼近地球所導致。而家我哋已經知道呢一顆巨大嘅行星係近100年天文學家不斷尋找其蹤跡嘅 Planet X。當時日華牧師已經分享，當 Planet X 逼近地球，其軌跡與地球同埋太陽連成一直線嘅話，就會令太陽爆發極為巨大嘅太陽風打向地球，即遙視者 Adams 所講嘅 Q Short。而另一方面，當 Planet X 逼近地球，其巨大引力亦都會帶嚟大量隕石，當中只要部分隕石擊中地球，都會為地球帶嚟災難。事實上，呢一種由隕石襲擊所留低嘅痕跡，其實我哋幾乎每日都可以睇見，因為當我哋望向月球嗰陣，單憑肉眼亦都可以睇見月球表面並唔平整，有住大小不同嘅凹痕。呢一啲其實就係由隕石撞擊月球表面所導致㗎。甚至唔使追溯到好遠嘅歷史，近代27年前嘅1994年，發生咗舒梅克李維9號彗星撞擊木星嘅事件，全人類親眼見證咗隕石撞擊嘅可怕。舒梅克李維9號彗星臨時編號 D/1993F2， 又譯作舒梅克李維9號彗星，或係舒梅克李維9。呢一顆彗星喺1994年7月中下旬同木星相撞，呢個係人類首次直接觀測到太陽系嘅天體撞擊事件，引起咗全球多間主流媒體關注，以及引發各地天文學家同埋天文愛好者嘅觀察熱潮。人們透過呢一次事件，更加了解木星以及其大氣嘅資料，以及木星喺太陽系內以強大引力扮演住清理太空垃圾嘅清道夫角色，使到地球上嘅複雜生命免受頻繁嘅天體撞擊影響。呢一顆彗星由美國天文學家尤金、卡羅琳、舒梅克夫婦以及天文愛好者大衛李維於1993年3月24日喺美國加州帕洛馬天文台共同發現，係佢哋發現嘅第9顆彗星。因此，根據國際星體命名規則，依照佢哋嘅姓氏命名。呢個彗星好可能係源於火星同埋木星軌道之間嘅小行星帶，隨後成為咗周期彗星。電腦推算運行軌道嘅結果顯示，係出自1994年7月8日，於距離木星表面4萬公里嘅時候，因為受到強大引力影響而分裂為21個小碎塊，並且喺格林尼治標準時間1994年7月16日20時15分開始，以每小時21萬公里嘅速度陸續墜入木星嘅大氣層，撞向木星嘅南半球，形成咗彗星撞木星嘅天文奇觀。於多塊碎片當中，以碎片 G 嘅撞擊威力最大，於7月18日7時32分撞向木星，威力達6兆噸 TNT 炸藥，其當量相當於全球核武器儲備總和嘅750倍，造成咗一條比地球直徑仲要長嘅疤痕。
The lasting impacts of comet Shoemaker-Levy 9. At the close of the last century, a comet captured into orbit around a planet traveled too close and was shredded by its gravity into multiple pieces, some as large as half a mile or 1 kilometer long. Those fragments would plunge into the planet's atmosphere in a series of impacts. Would the impacts be spectacular, or would the comet fragments disappear without a trace? In July 1994, astronomers around the world watched with bated breath as the fragments of comet Shoemaker-Levy 9 slammed into the planet Jupiter. Dr. Kelly Fast was one of the impact's observers and is now manager of NASA's Near-Earth Object Observations program.
It was just incredible to watch. Such an impact event had never before been witnessed, let alone studied. Ground-based telescopes around the world and spacecraft like NASA's Hubble Space Telescope and even the Galileo orbiter en route to Jupiter were used to observe the impacts. The discovery of the comet by Carolyn and Gene Shoemaker and David Levy gave us about a year to plan our observations.
The impacts proved to be impressive. The fragments, some 21 in all, plunged into Jupiter's atmosphere over the course of 6 days. At impact, they were traveling at a speed of about 37 miles per second, or 60 kilometers per second, heating the atmosphere to at least 53,000 degrees Fahrenheit, or 30,000 degrees Celsius. Like the splash from throwing a rock into a pond, the impacts created giant plumes of material from Jupiter's lower atmosphere, which rose as high as 1,900 miles, or 3,000 kilometers above the cloud tops into the stratosphere. In the aftermath, the plume splashback scarred Jupiter's atmosphere with dark clouds of impact debris, which could be seen for months as they were gradually dispersed by Jupiter's winds.
唔單止月球同木星會受到巨大隕石嘅襲擊，其實地球亦都曾經多次受到隕石襲擊，並且帶嚟可怕嘅災難。例如，好多研究恐龍嘅科學家都認為，地球上嘅恐龍之所以被滅絕，係因為6500萬年前有一顆巨大嘅隕石擊中地球，令到地球嘅氣候同埋環境突變，最終令到所有恐龍絕種。隕石擊中地球而產生巨大災難嘅事件，更加唔止出現咗一次。地球曾多次受到巨大隕石侵襲，每一次都會喺地表上留下隕石坑，成為一個證據，證明地球曾經多次受到隕石襲擊。例如，地球上最明顯、最為人所熟知嘅隕石坑，係位於美國亞利桑那州北部沙漠入面嘅巴林傑隕石坑。據推測，形成巴林傑隕石坑嘅隕石係一顆直徑約50公尺嘅鎳鐵質隕石，其撞擊速度至少達到每秒幾公里，撞擊所釋放嘅能量相當於10兆噸黃色炸藥。更加近期嘅係2013年2月15日車里亞賓斯克小行星撞擊事件，於俄羅斯烏拉爾聯邦管區嘅車里亞賓斯克市一次小行星撞擊事件。當日約上午9時15分，隕石進入大氣層嘅時候，直徑約15米，質量約7000公噸，喺天空中留下約10公里長嘅軌跡。主要碎片擊中咗捷巴爾庫爾湖，事件中造成1491人受傷。
On February 15th, 2013, over Chelyabinsk, Russia, an asteroid heavier than the Eiffel Tower slammed into the atmosphere. And then, 30 kilometers above the ground, it exploded. This violent event was brighter than the sun, but so high up that it was silent for a full 90 seconds after the blast, which only made the devastation worse.
So you see all these videos of people, look at what was that? They see the smoke trail in the sky, and oh, that's amazing. And then, just when you think nothing's going to happen, the shockwave hits and it blows out the windows. 1,000 people got glass in their face and their eyes because they're looking through the windows.
The shockwave damaged thousands of buildings and injured 1,500 people. What makes the Chelyabinsk incident kind of embarrassing is that the very same day, scientists had predicted that an asteroid would make a close flyby of Earth. And they were right. 16 hours after Chelyabinsk, a similar-sized asteroid, known as Duende, came within 27,000 kilometers of Earth's surface. That's closer than satellites in geosynchronous orbit. But while they correctly predicted this close approach, they completely missed the unrelated asteroid that exploded over Russia. And the truth is, this happens all the time. We're really not that good at detecting asteroids before they hit us. Since 1988, over 1,200 asteroids bigger than a meter have collided with the Earth. And of those, we detected only 5 before they hit, never with more than a day of warning. With all our technology and all the telescopes across the Earth, not to mention the ones in space, why do we struggle to detect dangerous asteroids before they strike? What are the chances that a big asteroid will hit, wiping out most, if not all, life on Earth? And if we saw one coming, what could we do about it? Asteroids are the leftover debris from when our solar system formed. 4.5 billion years ago, rocks and dust clumped together into molten protoplanets. Inside, heavy elements, metals like iron, nickel, and iridium, sank into the core, leaving lighter silicate minerals on the surface. Some of these protoplanets grew into the planets we know today, but many more collided with each other, breaking into pieces. These pieces continued orbiting the sun and smashing into each other and breaking into even smaller fragments. These became the asteroids, which is why some of them are rocky, loose conglomerates of gravel-sized rocks called rubble piles, and others, from the cores of planetesimals, are mostly metal.
So this is an iron meteorite, and essentially it's the piece of a core of a small planetary body, like it's basically a small planet, that formed 4.5 billion years ago, differentiated, so the core material fell out, and then this thing was smashed apart by a collision with another asteroid. That's the oldest thing you'll ever see.
Most of the asteroids have stable orbits between Mars and Jupiter in the main asteroid belt, but some have made their way closer to Earth, and these are known as near-Earth objects. They are of greatest interest to us because of the threat they pose. In his last book, Stephen Hawking considered an asteroid impact to be the greatest threat to life on Earth. But finding asteroids is difficult for several reasons. Most are spotted by ground-based telescopes.
So what you do is you take a sequence of pictures, 1, 2, 3, 1, 2, 3, 4, and you look for essentially a moving dot. And it's moving because it's orbiting around the sun, whereas the stuff far away, the stars and galaxies, are not.
But you have to look carefully. Asteroids are not very big. They range from meters up to kilometers in size. And in the vast expanse of space, rocks like that just don't stand out. And even the small ones can be damaging. The Chelyabinsk meteor was only around 20 meters in diameter, roughly the width of 2 school buses. Plus, asteroids are rough and dark. They only reflect around 15% of the light that hits them. So our best chance to see them is when they're fully illuminated by the sun. And that's why over 85% of the near-Earth asteroids we've detected were found in the 45 degrees of sky directly opposite the sun. This is called the opposition effect, and it means there are likely more near-Earth and potentially hazardous asteroids that haven't been detected yet. Any asteroid approaching from the direction of the sun just can't be seen. This is exactly what happened with Chelyabinsk. So far, we have detected and cataloged 1 million asteroids, the vast majority of which are in the main asteroid belt. But 24,000 are near-Earth objects, ones that we need to keep a particularly close eye on, because even once you've detected an asteroid, it's hard to tell if it will hit the Earth.
So if you just discover an object and you only have data from a few days, then you can't really tell where it's going to go, because you're trying to take this little arc of motion and predict it far into the future. So what you need is observations over years and years. But even if you have perfect observations of an asteroid, there's kind of a fundamental limit to how far in the future you can predict. And that's because a couple of effects. But one is that, they're not just orbiting the sun with no other influence. All of the planets have gravity, and all of the planets are pulling on near-Earth asteroids and can change the orbit significantly. So there is something called dynamical chaos, which basically means after a certain amount of time, you don't know where the asteroid is going to be. And in practice, what that means is we can't do any work more than 100 years in the future. So the maximum time you can predict with any accuracy at all where a body will be is about 100 years.
And this is pretty important, because we know with certainty if one does hit, the results will be dramatic. This is Barringer Crater in Arizona. It's named after mining engineer Daniel Barringer, who was the first to suggest it was formed by a meteorite impact. The prevailing view, even up until the 1950s, was that it was created by volcanic activity. But Barringer was convinced it was the site of an iron meteorite impact. So in 1903, he staked a mining claim and began drilling for the metallic meteorite, which he believed to be worth more than $1 billion 1903 dollars.
Yeah, so people are motivated by money, right? So they thought, hey, we can get some iron for free, basically. So they started to drill in the bottom of the crater and found nothing. And then they started to do other exploratory drills, and this went on for years and decades. They started to drill sideways. Somebody said, maybe it came in from an angle, which it did, and maybe the iron is not under the middle, but maybe it's over there under the wall. So he was doing drilling. If you go there, you can see the drills now. He was drilling around the wall, he found nothing. So what they didn't realize is when you have an impact at high speed, it's not like you're throwing a stone into a brick wall, and it makes a hole and sticks in there, or just bounces off. It's explosive. It's like totally explosive. So the kinetic energy of the projectile comes in maybe 30 kilometers per second. The kinetic energy of the projectile is big enough to completely vaporize the projectile. It turns it into a gas. And that gas is super hot and super high pressure. And it explodes and it blows out the crater. So the projectile doesn't really exist after the impact. Little pieces can survive. But this 50-meter body was basically obliterated. So he was looking for something that did not exist.
He spent 27 years mining the crater, drilling down to a depth of over 400 meters. But what he was searching for had vaporized on impact 50,000 years earlier. The 50-meter asteroid, not that much bigger than Chelyabinsk, released the energy equivalent of 10 megatons of TNT. That's over 600 times the energy of the Hiroshima bomb. So the thing that most closely resembles a meteorite impact is a very large nuclear explosion.
This is the actual size of the T-Rex skull. And I thought, this is such a cool thing, I gotta have it. So I bought the T-Rex. The dinosaurs were wiped out by a 10-kilometer sized asteroid that hit about 65 million years ago. So above a critical size, which is probably a couple of kilometers, an impactor delivers so much energy that it has a global effect. So essentially it launches a whole bunch of debris into suborbital trajectories. So the ejector goes around the Earth, falls back into the Earth, all over, even on the other side of the planet from where the impact occurred. And what that means is the whole sky lights up with wall-to-wall meteors. So you can imagine the sky turning from, a nice blue day like today into essentially a red-hot glow, like being inside a toaster oven. So the first effect of this impact, apart from the initial blast near where the actual impact occurred, the first effect is the sky turns into a great source of heat, and it cooks everything on the ground. So these guys were basically cooked.
Cooked alive.
Cooked alive as they were walking around. The only animals that had a chance were the ones living in tunnels under the ground, or maybe in the water. And they were able to come back and take over without having to deal with the dinosaurs as a major obstacle.
What are our chances that Earth gets hit by another 10-kilometer or bigger asteroid?
In your lifetime, assuming you live to be 100 years old, you have a 10-kilometer impactor like the KT extinction event every 100 million years or something like that. So the probability of getting it in 1 year is 1 in 100 million. So you have 1 in a million chance of dying from a 10-kilometer impactor. But because we know that there are no 10-kilometer impactors with a path that intersects the Earth for the next 100 years, your chance of dying from that is actually 0. So work done already has reduced that down, from 1 in a million to nothing.
So the good news is there won't be another dinosaur-style extinction event in our lifetimes. But there are exponentially more asteroids of smaller sizes. For every 10-kilometer asteroid, there are roughly 1,000 1-kilometer asteroids, and they're still capable of doing a lot of damage.
1 or 2 kilometers is capable of causing local but massive damage. So that means, instead of wiping out the entire world, you would wipe out the equivalent of some European country, like France or Germany, to mention 2 of my favorites. So you would obliterate those countries with the impact of a 1 or 2 kilometer sized body.
Do we know about all the 1 to 2 kilometer bodies that could hit us?
We think that we know 90-something%, maybe 98% of those bodies have been identified, and we have their orbits, and we can make reasonable predictions for the next 10 years or something about where they'll be. And we seem to be okay at the moment. But, what about the ones that are just a little bit less than a kilometer? What about the ones that are 800 meters? That's still pretty savage if it hits.
And this is possibly where the greatest threat of asteroids remains. A few hundred meters is large enough to obliterate a large city, but small enough that we haven't detected them all yet.
We're missing a lot of 100-meter-sized projectiles, and those guys are big enough to cause substantial damage on the Earth, depending on where they hit.
So it could destroy a city?
Yeah, it would knock down the buildings in the city, it would cause citywide fire, and if it hit the ground, it would throw up ejecta that would come back down and rain on the ground. It would be high-speed ejecta that would obliterate a 100-kilometer zone around it.
And this could happen tomorrow?
Well, it could, yeah.
If we saw a big one coming, what's our best bet for, could we do anything about it? What would we do about it? Is there anything we can do to actively...
No, there's nothing we can do. I was on a committee that looked at that, like 10 years ago. Like, what could we do? One option would be to try to bomb it. It's the standard thing. We don't know how that would work out. Even when you got it there, and even if you could explode it on the surface or in the surface, it's not clear what you would do, because typically what happens is you blow up a body and the fragments move out, they expand out, but not very quickly, and then gravity pulls them back together again. So it would reform as a rubble pile if it was not already a rubble pile to begin with, which it probably would be because of past impacts. So blowing up a rubble pile is something that we don't really know about. Another idea is you could be all gentle and attach a rocket to the asteroid and just try to push it aside. Let's nudge it aside. Instead of trying to blow it up, let's just push it gently aside so that it deflects it and it doesn't hit the Earth. The trouble is, when you work out the numbers, none of the rockets that we have can push it around enough. You would have to keep the rockets attached to the surface, which we don't know how to do. Remember, it's a rotating body for centuries to have a significant effect on the motion of the asteroid. So forget bombs, forget attaching rockets. Ablating the surface, basically you boil the surface with a laser. We don't have any lasers powerful enough and probably can't make lasers powerful enough to do that from the Earth. We would have to take the lasers to the object, which is even more difficult. The idea that you could wrap an asteroid in cooking foil, aluminum cooking foil, is another nice one. That may be a good one, the best one, but it still doesn't really work because we don't know how to do that. We don't have a way to launch enough cooking foil to wrap up an asteroid and change its radiative properties, which would itself move the asteroid around. So the truth is, to be honest, we do not have a way now to deflect a kilometer-sized asteroid at all.
That could destroy a country.
Yeah, we just don't have a way.
And 10 kilometers?
10 kilometers is absolutely 1,000 times more hopeless. So when we discussed this, we had all these grand ideas. Oh, we could do this, and none of them worked. We came down to the most basic idea. Well, maybe if we could figure out where the asteroid is going to hit, like which city is it going to explode over, we can evacuate that city. And then we looked at the history of city evacuations, and we looked at cases, where, for example, you have like a week's warning where some hurricane system is going to come in and flood a city. And evacuation just doesn't work either. And the reason is very, very simple. Like going into a city, there are not that many freeways. If you have millions of people trying to get on a freeway, the first time a car breaks down, you block that freeway. So instantly you have millions of people trying to get out of the target zone, and they won't be able to because all of the roads will be instantly blocked. So again, even evacuation of a city is probably the most hopeful thing that we could try to do. Even that's really, really difficult because of the large numbers of people involved. What I think all reasonable people would conclude is, let's do the thing that we can do first. So let's look for them. Let's do the surveys. Let's build the telescopes. Let's put this telescope in space. That will be a major contribution to understanding the threat from the asteroids. And then, when we find a particular object that looks especially dangerous, then we can focus on it. We can focus everything we have on it. And we can begin to think seriously and with real motivation about ways to deflect it.
就正如啟示錄所預言，喺大災難最後嘅1260日，地球至少將會受到2次巨大隕石襲擊，而呢2次隕石襲擊極可能正如上述影片所提及，大小約1公里甚至更大型嘅隕石，直接擊中地球嘅陸地同埋海洋，引起巨災。啟示錄8章5至11節，天使拿着香爐，盛滿了壇上的火，倒在地上，隨有雷轟、大聲、閃電、地震。拿着7支號的7位天使就預備要吹。第一位天使吹號，就有雹子與火摻着血丟在地上，地的1/3和樹的1/3被燒了，一切的青草也被燒了。第二位天使吹號，就有彷彿火燒着的大山扔在海中，海的1/3變成血，海中的活物死了1/3，船隻也壞了1/3。第三位天使吹號，就有燒着的大星，好像火把從天上落下來，落在江河的1/3和眾水的船員上。這星名叫茵蔯，眾水的1/3變為茵蔯，因水變苦，就死了許多人。